Before we continue with our next part, I would like to remind you of some of our standard graphing techniques or graphing ideas. Consider the function y equals x. Now we know that's the line that goes through the origin and is at an angle of 45 degrees, gradient 1. If we're asked to sketch the function y equals x plus 1, then that's the same line that has been shifted to the left by 1. Okay, so I'll attempt the graph of y equals x. Now that graph for y equals x plus 1 is a line that's parallel but has been shifted to the left by 1. We usually talk about it being shifted up by 1, but you can perceive that as being shifted to the left by 1. And we know that the graph of y equals x minus 1 is shifted to the right by 1. Or we tend to talk about it moving down by 1. Another point to make is for a circle, for example, x squared plus y squared equals r squared. That's a circle center 0, 0. But x minus h squared plus y minus k squared equals r squared is the same circle, but it has been shifted. Its x values have been shifted to the right by a magnitude of h, and its y value has been shifted up by a magnitude of k. So keep those ideas in mind as we move on to our complex numbers. Let's look at a basic case. Let's say we want the locus of a point that follows the following rule. The modulus of z is equal to 2. Now, thinking back to what modulus of z is, that's square root of its real value plus squared plus its imaginary value squared. So you can see that that's a circle. X squared plus y squared equals 2 squared. Circle center 0, 0, radius 2. So that's our basic case. What happens if the question was now the locus of a point that follows the following rule? Minus 1 plus 2i is equal to 2. We can rewrite this as z minus 1 minus 2i. This means that the real part of the center of that original circle we had from here has been shifted by 1 and its imaginary has been shifted by 2. So this results in a circle of center 1, negative 2, but radius remains the same.
Another way of looking at this is by recalling that modulus represents the length of a vector. In this case, we have a resultant vector that's the product of the vector 1 minus 2i being subtracted from z. So think back to our vector subtraction. When we subtract two vectors from each other, the resultant is a third vector. And in this case, we're looking at the length of that vector. So in this case, we have one vector, z, which is a moving point, and another vector, happening at 1, -2. So here's my real axis, my imaginary axis, and 1, -2. So recalling from at vector subtraction, for example, if z is the point here, then when we do that subtraction, our vector resultant is this, and we need that to be no more than 2 or no less than 2. So we know what that's going to look like. That's going to give us a circle of radius 2, as we discussed earlier. So we end up with this circle. The third way to look at this question is to replace z with x plus iy. Now if I collect the real parts and the imaginary parts, plus 2, then I end up with x minus 1 squared plus y plus 2 squared equaling 2, which is a circle, center 1, -2, and radius 2 as our usual circle equation.